3, graphing circular functions. The first graph we're going to take a look at is a sine graph. So here I have a table of values. I've got theta ranging between negative 2 pi going through to 2 pi, and they're in increments of pi on 4, as can be seen. And then we have the corresponding sine of those angles. So the angles, of course, given to us are in radians. So if we create this table of values, either using our CAS calculator or scientific calculator, we're able to graph those points, and it will form that shape there. The key to this is if we start from 0, so an angle of 0, then we have some critical values for the sine graph. So we have the position 0, 0, and then as we travel through pi on 2, we have the position pi on 2, 1, pi, 0, 3 pi on 2, negative 1, and then finally 2 pi, 0. Looking at our unit circle interactive, then what we've got here is point P, and that moves around the unit circle. But what I want you to focus on is how this point down the bottom here in red moves as the point P rotates around the unit circle. So we begin here at our critical value of 0, 0. After sweeping an angle of pi on 2, we had the position pi on 2, 1. And remember, the sine of the angle theta is equal to the y value, so it's making sense. Then on our sine graph, we have the position 0, 0 after an angle of pi has been swept. We've now swept an angle of 3 pi on 2, and at that position, sine of that is equal to negative 1, as shown on the graph. And then after we've completed one full revolution of the unit circle, we have swept an angle of 2 pi, and we return back to 0. With the sine graph, this theta axis here just represents the median, so that's the average overall. And then we have the maximum and the minimum. And we also have a period for the graph. So you can see here that it takes 2 pi for the graph to begin to repeat itself. So after that, after 2 pi, we get the same pattern repeating. So we go from 0, 0, get to the max, come back to the median, go down to the minimum, and then get back to the median. Then after that, it repeats. So that's a sine graph. We can do the same thing for cosine. And so again, generate another table of values. If we plot those, we get this basic shape. And let's look at the critical values for cosine. They're just a little bit different than the sine, but it follows the same kind of pattern. Except for instead of starting at the median, we start at the maximum. So our first critical value is 0, 1, then pi on 2, 0, pi, negative 1, 3 pi on 2, 0, and then 2 pi, 1. After that, it begins to repeat itself. So we can see a period again of 2 pi. That's how long it takes to do one full cycle of the graph. You can see that the median is on the theta axis, so our median here is 0. We have a maximum of 1, and we have a minimum of 1. We say that the amplitude is equal to 1. So that's how much we are above or below the median. It's the size of the wave. So we don't go from negative 1 to 1 and say it's got an amplitude of 2. It's the distance that the peak is above the median, and that's 1. So this summarizes everything for us. Our amplitude, so it's from the median to the peak, 1. How long does it take for the graph to begin to repeat itself? And you can see there it's 2 pi. Now, just like any kind of graph, there's variations of the standard sine and cosine. If we have y equaling a sine of nx and y equaling a cos of nx, the amplitude will be equal to the value that's in front of the sine or cosine. all right, so long as that's greater than 0. So if you've got a negative value in front, we just ignore the sign and look at the number itself. So we take the magnitude of that. And that will tell us the amplitude. It's the size of it, not the actual, don't take into consideration if it's a negative value. That will be a reflection, and we'll deal with that in a different way. So that's our amplitude. Our period will be 2 pi on n. So if, for example, if we had y equals sine of 2x, the value immediately in front of the x is a 2. So therefore, our period will be 2 pi on 2, which would simplify to being just pi. If n is greater than 1, then basically our wave will be compressed. So it'll take us less to get through one full cycle of the graph. If n is less than 1, then our graph will be stretched. So think about that. If we had y equals sine of 0.5 of x, then our period will be 2 pi divided by 0.5, and that would equal 4 pi. So it will take 4 pi for us to cover one full cycle of the graph. So you can see there that that has been stretched. Same thing applies for a. So this shouldn't be too difficult for you given all the work that we've done previously on graphs. But if a is a value greater than 1, then we're stretching it vertically. And if it's less than 1, then we're compressing it vertically. And the dilations, we describe those in the same way we did with all our other type of graphing. All right, so our first problem. Sketch one full cycle of the following functions. State the amplitude, period, and range. So let's look at A. We've got f of x equals 2 sine of 3x. Here's how we should begin. We set ourselves up with a bit of a grid, and in it we put the critical values, so that's the x and the y. So for a sine graph, we start at 0, 0, then pi 2 and 1, pi and 0, 3 pi on 2 and negative 1, 2 pi and 0. So we always do it that way. They are the critical values for a sine graph. Now, we've got a 2 out the front. That means that every y value has been multiplied by 2. So 0 times 2, 1 times 2, 0 times 0, negative 1 times 2, and so on. And we get those values. Now the value immediately in front of the x is a 3. That represents a dilation factor of 1/3 from the y-axis. That is, every x value has been multiplied by 1/3. So we've got the x values here, and we just need to multiply all of those by 1/3. So 0 times 1/3 is 0. Pi on 2 times 1/3 becomes pi on 6. Pi becomes pi on 3. 3 pi on 2 becomes pi on 2. And 2 pi becomes 2 pi on 3. Next, we set ourselves up with the axes, and we put in the critical values and mark them in. So we've got y ranging between negative 2 and 2. So I've got to show that in on the y-axis. And then I just space out the angles, and they'll be equal distance apart, and I just need to label what each of these points are, just going by our grid here. So you can see 0, pi on 6, pi on 3, pi on 2, 2 pi on 3. And then, of course, I follow the basic sine graph. So we start at the median, go to the max, go back to the median, go to the min, go back up to the median. And that shows one full cycle. B, same kind of, I was also asked to state the amplitude, period, and range. So the amplitude is 2. That is just the magnitude of the number directly in front of the sine part. The period is 2 pi on n, where n is the value immediately in front of the x. And so you can see there that it becomes 2 pi on 3, which makes sense because if we start at 0, it takes us 2 pi on 3 for us to achieve one full cycle of the graph. Our range is from negative 2 up to 2, and I'm including those values, so therefore it's square brackets. Let's now have a look at B. So just to refresh ourselves, B is f of x equals negative 3 sine of x on 2. So again, we begin by ruling up the grid with the x and y values in. And again, the critical values for sine, 0, 0, pi on 2, comma 1, pi, comma 0, 3 pi on 2, negative 1, 2 pi, comma 0. We have an amplitude, for this case, of 3, but the value in front of the function overall is negative 3. So I need to take every y value and multiply it by negative 3. And there's the results. The value immediately in front of the x in the function was a half. So x on 2 can be written as a half times x. So the value immediately in front of the x is a half. So in that case, I need to multiply by 1 over a half, and 1 over a half becomes 2. So I need to multiply every x value by 2. If I do that, it's shown here. So it's that point there, 0, 0, pi, negative 3, 2 pi, comma 0, 3 pi, comma 3, 4 pi, comma 0. They are the points that we need to plot. So again, I rule up my axes. On the y-axis, I put the points that I need, or the places that I need. X-axis, I label them from the far outside, so 0, pi, 2 pi, 3 pi, 4 pi. And this time, I follow the pattern, but because I've got a negative out the front, it's the sine graph that has been reflected in the x-axis. So it's that kind of shape, but upside down. So if you can't visualize that, that's fine. You can just simply plot the two outside columns. So 0, 0 goes there. Pi, comma, negative 3 here. 2 pi, comma 0 there. 3 pi, comma 3. And then finally, that last row, 4 pi, comma 0. So if you have a sine graph that's been reflected in the x-axis, the pattern will be median, minimum, median, maximum, median. The amplitude is the magnitude of the number that's outside the front of your function. So the magnitude of negative 3, which is just 3. Note please that we never have a negative amplitude. We're just talking about the size of the wave, so it's always a positive value. The period is 2 pi on n, so we've got 2 pi over a half. So it's 2 pi times 2 on 1, which is 4 pi. And our range, our y values will range between negative 3 and positive 3, including those values. Just making it really clear why we're multiplying by 2 here. N is equal to a half, so we're dilated by a factor of 2. That is 1 over a half. Think about it, how many halves would fit into 1? There'd be 2 of them, so that becomes 2. And it's from the y-axis. Now we're looking at cosine. We're going to use a very similar approach. So the first function here is a. So we've got f of x equaling negative 2 cos of x on 3. So our x values, the critical x and y values, so the x's are the same, so 0, pi on 2, pi, 3 pi on 2, 2 pi. But for a cosine graph, we start with the maximum, 1, go to the median, 0, then the minimum, negative 1, back to the median, 0, and then finish off with our maximum, which is 1. So they are our critical values for cosine, basic cosine. All right, we've got a negative 2 out the front, so we need to multiply every y value by negative 2. And that's what they equal. And we've also got its cos of x on 3, which is the same thing as taking 1/3 multiplied by x. So the number immediately in front of the x is 1/3. So I want to take every x value and multiply it by 1 over 1/3. And again, 1 over 1/3 will become 3. So I want to take every x value and multiply it by 3. And so this is the result after multiplying the x values by 3. And then finally, I set up my axes and plot the points. So it's the outside column. So it's x equaling 0, y equaling negative 2, x equaling 3 pi on 2, y equaling 0, and so on, just working down. And I'll get that shape. Not surprisingly, it's an inverted basic cosine shape. And the reason for it is that I have a negative out the front. Our period is 2 pi on n, so it's 2 pi over 1/3, so it's 6 pi. It takes 6 pi for us to begin to repeat the cycle, or repeat the wave. The cycle is achieved over 6 pi. The amplitude is just the size of the number out the front, so it's the size of that -2, which is 2. Our range, we vary between -2 and 2, including those values. The second graph, we've got f of x equaling a half cos of 4x. So we form our grid, put in the critical values for cosine. Out the front, we have a half, so every y value is multiplied by a half. The number immediately in front of the x is 4. So I want to multiply every x value by 1 on 4. And I get those. I then rule up an axis, get the y scale correct, get the x scale correct, and then place, or just put in the points from the two outside columns. So 0, a half, pi on 8, 0, and so on. And just remember, why we're multiplying by a half and why we're multiplying by a quarter, this represents the dilation factor. So dilated by a factor of a half from the x-axis and dilated by a factor of a quarter. That is, it's 1 over 4 to get that quarter from the y-axis. In the question, we are required to give our period, so it's 2 pi on n, 2 pi on 4 equals pi on 2. So to achieve one full cycle, it takes us pi on 2 to get there. Our amplitude is a half, so this is the distance between the maximum and the median. And our range, our y values vary between -1/2 and a half. Just looking at my graph here, I've been a little bit clumsy because over here I shouldn't be going all the way up to 1, I should just be going up to pi on 2. That's pretty bad. And actually over here it should be going through the median. So the first part of this graph is correct, but then my next point should be here, and then the point after that should be there. So this last part should flow through like so, and then finish there. Apologies for that. Now we've got an example where there is a domain restriction. So function f has a domain that we begin at 0 and go to 5 pi on 3. We're excluding the 0, but we're including the 5 pi on 3. The rule is f of x equals 2 lots of sine of 2x on 3. We need to sketch it and also state the range. Just getting out some key bits of information to begin with. Our amplitude is equal to 2, so we just take the size of that. N, the value immediately in front of the x, is 2/3. So 2x divided by 3 can be rewritten as 2/3 times x. So n is 2/3. Our period is 2 pi on n. So it's 2 pi divided by 2/3, which is the same thing as saying 2 pi multiplied by 3 on 2, which equals 3 pi. So in order for us to complete one full cycle of that rule there, it'll take 3 pi to do so. Now what's interesting for us is to try and get a bit of a feel for where 5 pi on 3 is. So we're going from 0 to 5 pi on 3. 5 pi on 3 is approximately equal to 1.67 pi. So we could rewrite that as being 1 2/3 of pi, but it just gives you a feel for what the number is, because otherwise, just looking at it, you may really struggle to understand where that is along the x-axis. So just sometimes listing the transformations is useful, particularly the dilation factors. So dilated by a factor of 2 from the x-axis. So just going back over here, every y value has been multiplied by 2. We are also dilated by a factor of 3 on 2 from the y-axis. So every x value has been multiplied by 3 on 2. That's 1 over 2/3, so that just becomes 3 on 2. So we apply those dilation factors to the critical x and y values. So the x's are multiplied by 3 on 2, the y's are multiplied by 2. And just so you can get your head around it, these are all just written as fractions involving pi here. Sometimes it's really helpful to convert those to decimals, just so you get a feel for where they would be. So 0, 0.75, 1.5, 2.25, and so on, going through. Our endpoints, so 0 is one of them. So x equaling 0, what is y? So we just substitute that into our rule. So it's 2 sine of 3 times 0, and that just becomes 0. So it's sine of 0. If we evaluate that, it's just 0. So it's 2 lots of 0, so 0. So when x is equal to 0, y is equal to 0. So we've got the point 0, 0. And then we substitute 5 pi on 3 for the next one. And then we've got 2 lots of sine of 2/3 of 5 pi on 3. So that becomes 2 lots of sine 10 pi on 9. And notice that this is not an exact value from one of the triangles, so we can't obtain, that is not an angle from one of the exact value triangles, so we can't provide an exact solution for this, so we're just going to leave it in the format of sine. So that's where that will finish up. But what we want to do here, guys, is plot the 2 outside columns on an axis, so that's what we show here. If we had one full cycle, it would be the full lot I've shown in green here. Okay, so that is from the grid, but I don't need that. I know that 5 pi on 3, that's it there, comma, 2 sine 10 pi on 9, that's the exact point where it finishes. So 0, 0 going all the way up and through to there. If we did one full cycle of that particular rule, we'd get back to this position, but that's not the case. We only want a certain section of it because there's a specific domain given. That's given there. But also I've made a little bit of a mistake because the domain given was circular bracket 0, comma, up to 5 pi on 3, square bracket. So this point here is included, so should be drawn as a solid dot, and this dot over here should be hollow. Our range, the lowest value that we have is here, and that is exactly 2 sine of 10 pi on 9, so that's obviously going to spit out a negative value. And then we go all the way up to the maximum, which is 2, so there's the range. So that's a pretty tough question for a Year 11 methods, but that's how you go about it. Now, I don't want to spend too much time on this table. It's just a basic summary of everything that you'll encounter at Year 11 and Year 12 for sine and cosine, and it all works the same as you'd expect. If you're talking about horizontal translations, then take whatever's in the brackets of the cosine or sine, make it equal to 0 and solve for x, and that will give you the horizontal translation. The k just shifts the graph up and down. A is your dilation factor running parallel with the y-axis. N is the dilation factor of 1 on n, parallel with the x-axis, so every x value has been multiplied by 1 on n. And that's all explained here. Your amplitude is just the size of the number immediately in front of the overall function. All right, so that's what the straight lines mean, just magnitude. Your period is 2 pi over the magnitude of the number immediately in front of the x. Your median is k. The max will always be whatever that median is, plus the amplitude, and your minimum will be the minimum minus that amplitude. So in the ones that we've seen so far, the median has been 0, so it's just adding the amplitude and subtracting the amplitude. So just a summary of the steps. Rule a wide T-shaped grid, and then put in the critical x and y values running vertically down it. So for sine, these are it. And for cosine, you put those down. Jot down the transformations in DRT order. Apply transformations on the x and y values working in the order of DRT. When dealing with fractions, it may be easier to add columns for workings instead of just doing the calculations mentally. And the reason for that is so that you don't make simple mistakes, particularly at the beginning of circular functions when you're not really used to this kind of stuff. And then plot the two outside columns on a set of axes. Be sure to consider the domain. Okay, so I'm going to leave A. I'm not going to explain A, but I will explain B. So we've got f of x equals negative 2 cos of x minus pi on 4 plus 3. So we've got a bit of everything going on here. Now what was out the front? Okay, so I'll stop it on that. And before I start that particular problem, I'll re-begin, and I need to, so just cut it back until where I finish the explanation of the box. So here we are for problem 4. We're going to sketch one full cycle of these functions, and they're involving translations, dilations. So first one, f of x equals 5 lots of sine of 2x plus 3. So straight away what we see here is a 5 overall out the front. The value immediately in front of the x is a 2, and then we're adding this 3 here. So there's no horizontal translation, but there is a vertical translation. We also have a dilation of 5 running parallel with the y-axis, and a dilation factor of a half running parallel with the x-axis. Let's go through and look at that. So for A, the amplitude is the magnitude of this number here, and so that's going to be positive 5. The period is 2 pi on n, so 2 pi on 2. And we get pi. Our median will be the part that we add on the very end here, so plus 3. So we're taking the whole graph, lifting it up by 3 units. So usually for a standard sine graph, the median will be at y equaling 0, but now the median will be at 3. So the median is 3. Our max will be 3 plus the amplitude, so the highest value we'll obtain is an 8. And the minimum will be 3 minus the amplitude, so negative 2. So straight away we know that our range will be from negative 2 to 8. We start with the critical x and y values for the standard sine graph and then work our way out. Notice that we have a dilation factor of 5 parallel with the y-axis, so we times every y value by 5. We then have a vertical translation of 3 units, so I add 3. So they will be my y values. Please note we do it in the order DRT, so dilations, reflections if there are any, and then translations. When we're multiplying, if that was a negative 5 out the front, then we could just multiply the whole lot by negative 5, and that would take care of the dilation factor of being 5 and also the reflection in the x-axis. You can do that in one spot, or you can just break it up. But very important you do dilations and then your translations last. X values, there's only one thing affecting the x values, and that's a dilation factor of a half. So I need to take every x value and multiply it by a half. And so now what I need to do is plot the two outside columns. So there's my graph. And I just put my positions in, put down what they're equal to, and then just follow that basic pattern. Please notice there's no reflections here. So for the sine graph, median, max, median, minimum, back to the median. Didn't ask me, but I could calculate the intercept for this as well. Alright, so now looking at part B of problem 4. Got f of x equals negative 2 cos of x minus pi on 4 plus 3. So firstly, there's a dilation factor of 2 parallel with the y-axis, so ignore the sign for the dilation factor. There's no dilation factor parallel with the x-axis. There's a reflection in the x-axis, so in effect every y value will be multiplied by negative 2. There is no reflection in the y-axis, so the x values aren't multiplied by anything for here. We are translated 3 units up, and we are translated pi on 4 units to the right. So to work out that horizontal translation, I just take whatever's inside the bracket, make it equal to 0, and solve for x. So let's take a look at the solution for b. So I'm scrolling through now, a for b. Amplitude, the value in front of the function overall was -2. I take the magnitude of that, that's equal to 2, so that tells us the size of the wave, the distance between the median and the maximum. The period is 2 pi on n, and that just ends up being 2 pi, so there's no compression or stretch horizontally. Our median was 3. Remember that the whole graph was moved up 3 units. Our max will be the median plus the amplitude, and our minimum will be the median minus the amplitude. So we range between a minimum of 1 and a maximum of 5. So there's our range, including the values, so square brackets. We begin by ruling up a grid, and we put in our critical x and y values for cosine. Dilation factor and also the reflection taken into account by just multiplying by -2. So the y values become this. Then we're translated 3 units up, so I add 3. Working the other way with the x's, there is no dilation factor with the x's, so all I need to do is add pi on 4 units because there is a horizontal translation. So I'm adding pi on 4. And because basically we're involving fractions here, it's a little bit more work. So I'm showing you quite a lot of columns. Now, if you're really good with dealing with fractions in your head, then go for it. But if not, I suggest that you start setting it up in this way so that you don't make mistakes. All right, so we're adding pi on 4. So I'm taking each of these x values and add pi on 4 to it. In this column of workings, all I've done is made sure that everything is over 4. So I've just converted all of these figures here so that they're on 4. So as an example, 2 pi is the same thing as 8 pi on 4. 3 pi on 2 is the same thing as 6 pi on 4, and so on. Now I can combine the fractions. And in this case, there's no simplification needed, but it is possible that I could have another column of workings where I simplify things. So those are my angles, they are the x values, and these are my y values, which I want to plot on a set of axes. So I place those positions. Notice that the jump between each increment here is 2 pi on 4. So I'm going from pi on 4 to 3 pi on 4, then another jump of 2, 2 pi on 4, 7 pi on 4, 9 pi on 4. So that helps you with where your starting point is along the x-axis. Your y values are pretty easy to work out. And then I just place the points from the grid above. Done. Now it did say for 1 full cycle, I think. Yep, 1 full cycle. So that's done there. Finished. Okay, problem 5. Sketch the graph of this and state its domain and range. So we've got everything going on now. It's as complicated as it gets. Our amplitude is just the magnitude of that 3. The number immediately in front of the x is 2. So the period will be 2 pi on 2, which just becomes pi. So it takes us pi to cover 1 full cycle of the graph. Our median is -5, so that's a part that we're adding on at the end. Our maximum will be our median plus the amplitude, so -2. And our minimum will be the median, median minus the amplitude, so -8. So our range will be from -2 through, -8 up to -2. Transformations in order DRT. We are dilated by a factor of 3 from the x-axis. So every y value has been multiplied by 3. We are dilated by a factor of 1/2 from the y-axis. So every x value is multiplied by a half. We are translated 5 units down, and we are translated pi on 6 units to the left. And this is why it's so easy to just take whatever's inside the brackets, make it equal to 0, and solve for x. So we have 2x plus pi on 3 equaling 0. Solving for x, we get x equaling negative pi on 6. That represents a movement in the negative direction along the x-axis. So it's a movement by pi on 6 to the left. So we begin by drawing up our grid. We've got the critical x and y values for a sine graph. And we'll sine. Dilation factor of 3 running parallel with the y-axis or from the x-axis. A translation of 5 units down. Working with the x's now. Dilation factor of a half from the y-axis or parallel with the x-axis. A translation of pi on 6 units to the left, so we take away pi on 6. And so you can see there I've got 0 minus pi on 6, pi on 4 minus pi on 6, and so on. I now put all of those fractions over a common denominator. So what I've chosen here, because I've got 4s and 2s and 6s, I've decided to put them all over 24. I then do each of these sums and they're all over 24. Where possible, I simplify. So what I'm interested in doing is plotting these and these. So here's my axes. There's my critical values. Notice, guys, to get a feel for what you're jumping up by on the x-axis, it's best to go and have a look at this column here. So I'm going negative 4 pi on 25 on 24, 2 pi on 24, 6 pi on 24. So you can see there each time it's a jump of 6 pi on 24. So that allows us to space set out along the x-axis, but don't put these values in with a denominator of 24. Instead, put them in their simplest form. Then just put in the corresponding y values, and away you go, it's done. Please note that there was no domain restriction here, and there was no request to just sketch one full cycle. Therefore, our domain is R, and I've shown that with our arrows showing that the graph continues on in either direction following that shape. Our range is between negative 8 and 2. That should be from negative 8 to negative 2 there, guys, not positive 2. So negative 8 to negative 2. Okay, so problem 6, given that f of x equals 3 lots of cos 2x plus 1. We need to state the transformations that would be required to move g of x, which is the basic cosine function, to become f of x. So we have a dilation factor of 3, parallel with the y-axis, or in other words, from the x-axis. We have the dilation factor of a half, parallel with the x-axis, or from the y-axis. There are no reflections. There are no horizontal translations, but there's a vertical translation of 1 unit up. B, sketch each transformation in the interval 0 to 2 pi. So over 0 to 2 pi, we need to sketch each one of those transformations described. Okay. Apologies for the messiness of this, I am left-handed. Okay, so let's look at the green graph. That's the basic y equals cos x. So the critical values are given. The first transformation that we're going to consider is a dilation factor of 3 parallel with the y-axis, and that's shown here in blue. So every y value on the green graph is multiplied by 3. So this position here comes there. Here it's 0, so it's going to be multiplied by 3, so it remains 0. Here we have negative 1 on the green graph, the original graph. So dilation factor of 3 parallel with the y-axis, we just multiply by 3, becomes -3, just remains 0, and the 1 becomes 3. So that's the first transformation handled. The next one is that we have a 2 immediately in front of the x. So that means that every x value is multiplied by a half. So again, if we are now looking at the blue graph, notice with the blue graph, over between 0 and 2 pi, we do 1 full cycle. So now if there is a 2 in front of it, we should get 2 full cycles, and that's what's shown in black here. So up, there's 1 full cycle, and now here's through to the second full cycle. So in blue, everything has been shifted across. Well, not shifted, I shouldn't say shifted, sorry. It's been compressed along the x-axis. And we're getting more of those waves through between 0 and 2 pi. So we get that black graph. And then finally, a 1 is added to the end of it. So we take that black graph and we shift it up 1 unit. So it describes everything that we see. See, we need to finally state the domain and range for that function given to us at the very beginning. So with our domain and range, we went between 0 and 2 pi. That's for 2 full cycles. And our range varied between -2 and 4. So we're looking at some tan graphs here. Again, let's generate a table of values, and you can do that just using your CAS calculator. If you plotted that, you'd be able to see that we'd get these shapes here appearing. Please notice that there's asymptotes everywhere with the tan graph. So if we just focus between -pi on 2 and pi on 2, you can see you've got asymptotes. And then we get this basic shape happening here. And if we move across to the right, you can see another asymptote exists at 3 pi on 2. And again, that shape appears. Now, usually when we're dealing with circular functions, we begin from 0 and go up to 2 pi, which is there. And in doing so, you'll see that asymptotes exist at pi on 2 and 3 pi on 2. I'm just going to try and make use of our unit circle interactive and see if I can explain to you why we get that shape and why the asymptotes exist. So here's our unit circle. Remember that the tan of this angle theta is defined as if we draw a tangent line here and extend the ray through to that tangent line. So we can imagine there's a tangent line at the position 1, 0. Where would this extend through to it? About there. So the distance between where I am and the x-axis will be equal to the tan of that angle. So in this case, it will be positive. Now notice that what's going to happen here as we keep on approaching an angle of pi on 2, remembering that the graph at pi on 2 is an asymptote. So again, imagine the tangent line being drawn through. You can see that if we extend this up, it's going to be very high indeed, way up beyond what's shown here on this screen. And as I move around, even higher, even higher, even higher. And as we finally achieve an angle of pi on 2, then what will be happening is that the extension of that ray will be running parallel with the tangent line. That is, that ray will never cross the tangent line, therefore the tan of that angle will be undefined. And that's what's shown here. So as I've just swept through, as I've increased the angle and approached pi on 2, the value of tan theta is getting larger and larger and larger. And if we move to pi on 2, then it's in fact undefined. Reason being is that the ray and the tangent line itself on that unit circle are running parallel with each other. Now let's move through beyond that. Again, the tangent line is here. How do I evaluate what the tan is? I simply reflect that ray back and see where it intersects that tangent line. So you can see where I am at the moment, it's going to be a very large negative value, and that's shown on the graph as well. And now as I move towards pi, where I am at the moment, if I just reflect back through, you can see it'll probably come into about there somewhere. So it's a fairly small negative value for tan of that angle that I've swept through. And again, that's shown on our graph here as we're moving towards pi. If I do get to pi, then I reflect back, then there's actually going to be no horizontal distance here, so it's going to be a 0. And that's shown there. And then I continue on in this third quadrant, and you can see that if I'm here, I'll move to this position. If I'm there and I reflect that ray back, comes to about there, and then you can tell it's going to intersect at that position here, and you're going to get yourself a positive value for tan. And that's shown here. And as I move this red dot towards 3 pi on 2, again we get to that asymptote, reason being the extension of the ray will be running parallel with the tan line, and at no stage will they intersect, and therefore tan of that angle is undefined, and that repeats it. That's a fair bit of information. It's not essential, but hopefully it helps you better understand how this pattern is formed based on the unit circle. Some key points. There's no actual amplitude for the tan graph. And if you take a look, how long does it take for this pattern to repeat itself? Well, it's done between negative pi on 2 and pi on 2. So there's a difference there of pi. So our period for a tan graph is in fact pi. That's how long it takes for us to repeat. And there is no amplitude because there's no actual wave to it. So for the basic tan graph, the effective A, that represents a dilation factor running parallel with the y-axis. The N, dilation factor of 1 on N, parallel with the x-axis. We have asymptotes at pi on 2n, 3 pi on 2n, 5 pi on 2n, 7 pi on 2n, etc. And we can also go negative as well. Follow that pattern through negative, so negative pi on 2n, negative 3 pi on 2n, and so on. The effect of A and N as far as compression and stretching are the same. And the big one for us is that the period, instead of being achieved with 2 pi on n, it's pi on n. And that's a common question that will be asked, just that knowledge there, that you understand that that's how long it takes. Alright, so question 7, state the period and sketch the graph of y equaling 2 lots of tan of x on 4. So for our period, the n value, the value immediately in front of the x is 1/4. So our period is pi on n, so it's pi over 1/4, and so it's 4 pi. That's how long it takes us to get there. Our assies we can write as being plus or minus pi on 2n. And so if we put that in and the value of n being 1/4, then we'll end up with plus or minus pi over 1/2, and then that will simplify, as you can see, to being plus or minus 2 pi. So there's our asymptotes. We put in our asymptotes, as shown here, minus 2 pi and plus 2 pi, and then we have our basic tan graph. Problem 8, f of x equals negative tan of 3x take 2. State the transformations that will be required from the basic tan graph to become this f of x over the interval of 0 to pi. So, A, we're dilated by a factor of 1/3 from the y-axis. So every x value is multiplied by 1/3. We are reflected in the x-axis. So every y value has been multiplied by -1, and we are translated 2 units down. 2 units down. Find the equations of all asymptotes over the given interval. So we want from 0 to pi. So the assies will be pi on 2n, 3 pi on 2n, 5 pi on 2n, 7 pi on 2n, and so on. N itself, the value in front of the x is 3. So you can see there that that will generate pi on 6, pi on 2, 5 pi on 6. I could keep on going to get 7 pi on 6, but 7 pi on 6 will be greater than pi, because pi itself is 6 pi on 6, so we don't need that asymptote. We only got 3. So now what I do is I put in the asymptotes, and I draw the basic tan graph, remembering that it has been reflected in the x-axis, so I just need to flip it upside down. So usually between two asymptotes, the shape would come up and around like so, but instead we need to be doing it this way. And just remembering the center there that's been brought down by 2 units, so that -2, so that's that point there where we start changing the direction. So there's my asymptotes, and I've got all the key bits of information in as shown. My domain, we go from 0 to pi, and I'm excluding the set that contains pi on 6, pi on 2, 5 pi on 6, just the asymptotes. And our range is we can have all real numbers. So we go on indefinitely up in that direction and indefinitely in this direction. Of course, we can show all this information in our CAS. It's not really a big surprise at all. Just make sure that you are in radian mode. That's the most crucial part. All right, so this is part of the study design. It's new in this study design, and the reason that we teach it here at Year 11 is that it is possible that you'll be given one of these kind of questions in an exam next year in Year 12. I think that you'll agree it's not a very useful idea, but it's a fairly easy one to understand. So basically, what the whole basis behind it is that sine of x will approximately equal x for small values of x, so values between 0 and 0.2. So we're looking at the angle changing between 0 and 0.2 when we're in radians. All right, so we've got the basic sine graph here, and as you know, it takes 2 pi for us to complete one full cycle. So we're halfway, and that's at pi, which is approximately equal to 3.14, and the full cycle is achieved at 2 pi, which is approximately equal to 6.28. It's pretty clear that at the very beginning of the sine graph, y equaling sine x is approximately equal to the line y equaling x. So in other words, what we can do is say that sine of small angles approximately equal that small angle. Of course, the angles need to be in radians, and that's the most crucial part. So if we just focus in on this part of the graph, it becomes more clearer to us. So there's the curve there, a very slight curve in blue, and you can see it's approximately equal to the line y equaling x. So as we continue further along, the approximation becomes worse because that gap becomes bigger. Here's an application. So calculate percentage relative error, correct to 3 decimal places in the approximation to sine x using x equaling 0.1. So we throw in 0.1 of a radian into sine x. What do we get? Well, sine x should be approximately equal to x. So sine of 0.1 should approximately equal 0.1. What does sine of 0.1 actually equal? Well, if we're going to be a bit more accurate, we'll throw sine of 0.1 into our CAS calculator, and you can see it's equal to 0.0998834, blah, 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 blah. So let's look at the error. We approximated that it would equal 0.1, but it's actually equal to that. There's a difference, a very small difference shown here. Now, what's the percentage error? It's the difference, how far we're out by with our approximation, divided by the actual figure, multiplied by 100 over 1. So you can see there that that is equal to 0.16686%. So it's a very close approximation. The question asks us to provide it correct at 3 decimal places, so first, second, third digit. The next digit is an 8, so I'm going to round that 6 there up to a 7. So it's approximately equal to 0.167%. That's correct to 3 decimal places. That's how close it was. So it was a very good estimation. Again, this major idea that sine of x is approximately equal to x only works for the smaller values of x, so at the very beginning of the sine graph. It's not relevant for anywhere else because obviously this line y equaling x extends through, so it's going to be way off when we're talking about these values. So